Hello. Now we are going to deal with bound states. Bound states, that is when particle is confined to move in a region. Suppose these are 2 points and in this region this particle is confined to move. This particle will not to move infinity on either sides. There is only limited region. Suppose this is point x1 and point x2. So these are called classical turning points. That is, whatever energy of the particle will be, it will reflect at these classical turning points, so that this particle will not to go infinity, but it will be bound between these 2 points. These bound states we can see in infinite square wave potential. Also in harmonic oscillator. Now we will deal with these two topics. First this one, and for okay, one more thing, for bound states we have two theorems. Theorem number first, in a one-dimensional problem, the energy levels of a bound state system are discrete and non-degenerate. Means whenever we will deal with such bound states, then energy level of this system will not allow all the energy levels. It will allow some specific energy levels, that is discrete, and also non-degenerate. Non-degenerate, that is for each energy levels, discrete energy levels, because there between these are not allowed. In quantum mechanics, as we know that in classical mechanics we have continuous energy levels, but in quantum this is discrete. And non-degenerate means for each energy level we will have one eigenfunction for each energy level. This is non-degenerate. And theorem number second, wave function psi n x, the wave function psi n x has these are for bound states and nodes. Nodes, that is when psi n x vanishes. So, if psi n x have n nodes, it means that psi n x vanishes n times. We also have read in particle in a box. What here? This is like this wave function has here one node, where the probability of the particle, the probability to finding a particle in this region will be 0. So, wave function has n nodes. When if n is equal to 0, correspond to ground state. And this will be n minus 1 nodes if n nodes for n is equal to 0, and n minus 1 if yes n minus 1, that is this is n is equal to 1, here n is equal to 0, here n is equal to 1, correspond to ground state. So, these are some basic theorems which will be applied in bound states. So, let us deal with infinite square well potential. Now, deal with infinite square well potential. In this, we have basically there are two parts. First is the asymmetric square well potential, that is with infinite asymmetric infinite square well potential, and second is symmetric. The symmetric infinite square well potential. Now, what is main difference? Here potential is of the form infinity 0 and infinity for x less than 0. This is for 0 greater than and equal to, and also when x will be equal to or less than a, and for this again greater than a. So, this is potential form in asymmetric infinite square potential. Yes. here Vx for symmetric, we will translate it by a by 2, then we get again only translation here. So, x less than minus a by 2, this is minus a by 2 to a by 2, and this is for greater. Now, we will consider first for asymmetric infinite discoverable potential. Clearly, for this reason and for this reason, wave function of the particle will be 0 for this and this. Wave function of the particle will be 0 outside boundary. Yes, you can imagine diagram of this also. This is infinite discoverable potential. This is on x-axis, so that the particle will confine to only this region. This is 0, this is a. So, this is asymmetric, and when we take origin here and a by 2 here and here minus a by 2, then that will be symmetric. Okay, but our main concern is asymmetric. Now, we will use Schrodinger equation for this reason. Classically, the particle will reflect at these two classical turning points, and obviously here is v is 0. It means that the particle momentum will be p is equal to under root 2m e minus v. So, that will be considered out only e, because that is kinetic energy. Actual this is Ek. What is Ek? Total energy minus potential energy. Potential energy is 0 for this reason. So, Ek will be E. Quantum mechanically, we will see that this bound state, that is a particle, will have only a discrete energy level as well as non-degenerate, that is there will be only one function corresponding to each energy level. So, now let us see. So, for region 0 to A, we will write to study dynamics of the particle, use Schrodinger equation. Del square psi upon del x square plus 2m upon h cut square e minus v psi is equal to 0. Since v is equal to 0 in region this, so this will be obviously 0, and taking k square is equal to 2m upon h cut square. So, this equation reduces to del square psi upon del s square plus k square psi is equal to 0. Taking solution of this equation, psi x we can consider yes, because in that region only there will be incidence on right side and again left side reflected. So, for incidence we can write this one, and for reflected we can write this part, because the moving particle there is the wave packet associated with moving particle. So, using these terms to show incidence and reflected part. This can also be written as in the form of sin and cos. So, this will be changed to a sin kx plus b cos kx. We can use this also. To calculate constants value, we need boundary conditions. So, what are boundary conditions? At walls, since there is reflection, so at x is equal to 0, wave function will be 0. Also at x is equal to a, wave function is 0, because these are turning points. So, applying this and this separately in this equation, what we get? We get, putting here x is equal to 0, so psi 0 is equal to a sin 0, that is 0, a into 0 plus cos 0, that is 1, so b into 1. So, this is again 0, 0, and this is also 0. This implies the value of b is 0, and putting this psi a is equal to 0, here we get psi a sin k a plus this b is 0, so 0 into cos k a, this term will be 0, and from here this is also 0 using boundary condition. So, a sin k a is equal to 0, that is, since a is equal to not 0, this implies sin k is equal to 0, and we know general solution, k a is equal to n pi, yn quantum number. So, denoting here also, that means the value of k, this is kn is equal to n pi by a. What is kn? This is put here 2 me upon h cut square is equal to n pi by a. This is the value of k square. So, we will square both terms. So, what we get E? E is n square pi square h cut square upon 2m a square. This energy level is same as, yes, energy level in a particle in a box using quantum number n. So, what we see that this energy is quantized. Energy is quantized, discrete energy levels, because E1 is equal to what? You can see E1 is equal to pi square h cut square upon 2m a square, and what is E2? This is 4 pi square h cut square upon 2m a square. So, this is allowed, this is allowed, but between this energy level, those energy levels will not be allowed. Like if we want to say 2 pi square h cut square upon 2m square is not allowed. Yes, but these are allowed. So energy is not continuous in bound state, as we have read in theorem first. That is done here. So only certain values of energy is permitted. Now dealing for wave function. Before calculating wave function, one more interesting point, that energy between adjacent levels this is not constant. You can see using formula, just find out En plus 1 minus En. Yes, this will be energy between adjacent levels. First is n and second is n plus 1, that is first is 1, then second is 2, like this in variable form. This is, as we have note down that En is equal to what? N square pi square h cut square upon 2m square, and for n plus 1 n plus 1 square pi square h cut square upon 2m square. Taking common, pi square h cut square upon 2m square in bracket n plus 1 square minus n square. So n plus 1 square is what? N square plus 1 plus 2n and minus n square cancel out. This is what? 2n plus 1. Okay. So this can be written as En is equal to n square pi square h cut square upon 2m square. So what is this quantity? This is En upon n square. Yes. So writing down En upon n square, and this is 2n plus 1. In more better way, En plus 1 minus En upon En is equal to 2n plus 1 upon n square. What we want to see, in classical limits, we know that there exists continuous energy level, so that n will be infinite in classical sense. So when we will take n infinite, then what is here? Limit n tends to infinite for En plus 1 minus En upon En is equal to limit n tends to infinite for 2n plus 1 upon n square. Obviously this will be 0. It means that the levels become so close together so as to be practically indistinguishable. Okay, so this is some short discussion for energy, and now treat with wave function. Wave function psi nx is equal to a sin kx plus b cos kx, and here we found that a sin kn, that is n pi by a. We have solved this one, into x and b0. So this is wave function. Now we will find a such that this wave function will be normalized. So for psi nx to be normalized, we use condition psi x dx is equal to 1 in region 0 to a. This is what? This is actually psi nx and its complex conjugate multiplication 1, and we can see that this is what probability of finding the particle in this region dx, that is 0 to a for here case. Now using his, since here is no imaginary quantity, so no effect, writing down 0 to a sine n pi by a x, and this will be a star sine n pi x upon a dx is equal to 1. Now we have to solve this one. So mod square 0 to a sine square n pi x by a dx is equal to 1, and we have solved this integration in particle inner box also. Yes, so obviously we will get mod is equal to under root 2 by a. So what is now wave function? What is normalized wave function? Normalized wave function will be psi nx, here is a, so putting under root 2 by a sine n pi x by a. So this is what we have get normalized wave function, as well as we have calculated its eigenvalues. Here the value of n is 1, 2, 3 and so on. This is quantum number. Now let us deal with some discussions. We can plot a graph for x and sin x, x sin x, since sin x is equal to under root 2 by a sine n pi x by a. So we can calculate for psi 1, psi 2, psi 3. Yes, I'm taking the 0, I'm taking negative x, this negative also. So it's for yn minus y under root 2 by a. Here amplitude is minus under root 2 by a. For psi 1, psi 1 will be psi 1 is equal to under root 2 by a sine pi x by a, forming this here, taking the 0 to a. So this will be like here, so joining like this, form here a line for magnitudes. Okay, this is for psi 1. After for psi 2, under root 2 by a sine 2 pi x by a. For this is here is a by 2, so we can form like this. For psi 2, next for psi 3, under root 2 by a sine 3 pi x by a. So for this taking here a by 4 something, or here 3 parts, a by 3, 2a by 3, 3a by 3. So taking a by 3 and here something 2a by 3. Then we can form wave functions 2a by 3 forming for psi 3. Yes, this is for psi 3. So what we see here, look, for here, yes, obviously these are nodes and these are now we have again nodes. These are nodal points for psi 2. For psi 2, what we have? We have one node here, 0 and a for all wave functions, because particles will reflect at the walls. But for psi 2, we have one node, where? At this point. For psi 3, we have two nodes. Yes, these are talking in between 0 and a. And we have read theorem that for bounded state psi nx has n minus 1 nodes when n is equal to 1 corresponding to lowest energy level. So this is what we have seen using diagram also. More 2 points. First is sine 2n plus 1x. These are even. From figure we can see that short for this is wave function, then drawing here, or you can extend here this wave. This is what? This is odd. But when we have like this, wave functions, so using this line we observe symmetry. So this is even. And also between 0 to a, this is also symmetry. So we have that is this is even. So for psi 2n plus 1x, this is even, and psi 2nx, this is odd. This is with respect to center of the well. Zero, a, drawing here, this is what? This is for, if you remember, this is for psi 2. That is for n is equal to 1, psi 2. This will be odd. For psi 1, if you will put n is equal to 1, for psi 2, this is odd. But if you will put here n is equal to 1, psi 3, this is even. What is psi 3? Psi 3 is this one, obviously, and this is even. So as same we can see for both wave functions. And also one more point, that the wave functions corresponding to different energy level are orthogonal. that is, if we take psi 1 and psi 2, these are wave functions, that is non-degeneracy, and there is only one wave function corresponding to each energy level. So, if you will take psi 1 and psi 2, so complex conjugate of one and taking second one, that will be 0, taking integration. So, for general orthogonal condition between 0 to a, if you will take different wave functions, that is, if we take psi m and psi n, and for one of them we take its complex conjugate, then it will be del mn. So, these are different, it means this will be 0. As we have seen that we have not taken n is equal to 0 because this is not admissible. For this is we get psi 0 and also energy 0. So, this is not interesting result. So, we will take n is equal to 1 for ground state. Now, so lowest or ground state energy, this will be for n is equal to 1, since En is equal to n square pi square h cut square upon 2m a square. So, E1 is equal to pi square h cut square upon 2m a square. This is what called 0 point energy. Okay, we will write this as ZPE. It means that there exists no state with 0 energy. Yes. Now, we can use for excited states. For excited states, we will use quantum number from 2 and so on. So, for excited state, En is equal to what? This will be, obviously this is Sm, and in short we can write that this is E1. So, n square E1 in short. Now, we want to study about 0 point energy. Discussion about 0 point energy. This is a very important topic. Now, as name suggests, 0 energy. This is what? If the particle has 0 energy, this is, suppose this is particle, in this region this particle, and this particle has 0 energy, then for 0 point energy, if you will see, this is the minimum possible energy. But main question is that will it be at rest inside the well? Obviously, name suggests that when this particle is in well, then will it be at rest inside the well? In that situation, when it has 0 point energy, if this statement exists, then that statement will violate Uncertainty principle. Heisenberg uncertainty principle. How it is? Let us see. Suppose we have confined a particle in the region 0 to x2a. It means that this particle acquire certainty in position. So, uncertainty in position. So, if you find uncertainty in position of the particle, what is order? Order will be delta x, and this is what? A. And we know that according to Heisenberg principle, this is so. If there is uncertainty in position, then there will be a minimum momentum uncertainty, which is h cut upon delta x comparable to h cut upon a. So, if particle is in this region, so it has uncertainty in position and also it has minimum potential and minimum momentum uncertainty. And if this is, then we also know that p square is equal to 2me or E is equal to p square upon 2m. Yes, this is kinetic energy, because kinetic energy Ek is half m square multiplying by m. So, this will be p square upon 2m. It means that if particle has minimum momentum uncertainty, it leads to minimum kinetic energy also. So, particle will be not at rest. This proves here. And if we will decrease the width of the well, then this quantity will increase. By decreasing A, that is, we are confining particle further and further, and by doing this, uncertainty in momentum will increase and particle will move faster and faster inside the well. And when it will move faster and faster, and we know that for 0 point energy, this is pi square h cut square upon 2m square for E1. So, decreasing A, confining particle further, increasing in uncertainty in momentum, and also increasing its 0 point energy. Conversely, if we will increase this length, then 0 point energy will decrease, but it will never vanish. So, 0 point energy, this reflect necessity of a minimum motion of a particle due to localization, and 0 point energy occurs in all bond state potentials. One more differentiate in classical mechanics and quantum mechanics, that lowest possible energy in this case and lowest possible energy in this case. Here this is the minimum potential energy, but this will be not only potential energy, but this lowest possible energy is sum of kinetic energy and potential energy. Very important point. So this is very important concept, and we apply this concept in microscopic world. Why in microscopic world? Because for quantum mechanics we know that lesser will be mass, greater will be wavelength, and for moving particle, for which is microscopic particle, wavelength is of higher order, and using concept of de Broglie, and then Schrodinger equations, dynamics of the particle can be studied. Some examples are here. If there is no 0 point motion, then what will happen? The atoms will not be stable. Second point, we know that helium do not freeze at a very low temperature. This is because of 0 point energy. So in microscopic world we have various physical consequences of 0 point energy. In microscopic, that is for more m, 0 point energy exists, but this is infinitesimally small, and we can see this about 0 point energy using some examples. Now let us see with the help of example what we want to see. We want to see variation in 0 point energy when we reach from microscopic world to microscopic. For this we are considering particle in an infinite potential well. So we will see by 3 cases. First, if we are taking 100-gram ball and this ball is confined on 5 meter long line. For point B, we will see for oxygen atom, which is confined to 2 into 10 power minus 10 meter lattice. For third case, we will see for electron, which is confined to 10 power minus 10 meter atom. So 0 point energy for 3 cases we will calculate. So obviously this is equal to h cut square pi square upon 2m square. The value of h cut we know, h upon 2 pi, and what is h? 6.6 into 10 power minus 34 upon 2 into 3.14. So from here we can calculate h cut by 3.14, 2 into what is mass? The value of m will be 100 gram, that is, this can be converted into kg, 0.1 kg, and this A will be in meter. Obviously this is 0.5. So by putting these values in this equation, we get 0 point energy of 1.25. This is 2 into 10 power minus 68 joule, and we will convert by dividing 1.6 into 10 power minus 19. This will convert in electron volt. So that value is 1.25 into 10 to power minus 49 electron volt. This is for microscopic. Come towards here. For this we will solve again this one. H cut will be same, but m will be what? What is m? This will be 16 into 1.6 into 10 power minus 27 kg. And this will be approx 26 into 10 power minus 27 kg. What will be A? A is 2 into 10 power minus 10 meter. So using again h cut this m and this A in this formula, we get E is equal to 0.5 into 10 power minus 22 joule, and in electron volt we get 3 into 10 power minus 4 electron volt. Knowledge difference, order of minus 49, order of minus 4. And for electron, m is equal to 9.1 into 10 power minus 31 kg, and A is 10 power minus 10 meter. So we will put this m and A and h cut in this formula again. So we get 0 point energy 5 into 10 power minus 8 joule, minus 18 joule, and this is equal to approx 30 electron volt. So what we want to show, that when we move from microscopic to microscopic, then 0 point energy is of more importance. Yes, we can see using these data in increasing order. Now let us see for short discussion symmetric potential well. For symmetric potential well, we have written potential for which is translated by A by 2, that is, we have written in starting of video. This is only translation by A by 2, so that it will be symmetric with respect to center of the well. You will see this. So taking here A by 2 minus A by 2 0, so this will follow symmetric. So symmetric potential well. For this we will calculate as same for asymmetric, and we will see that energy will be same, there will be no changes in energy, because the Hamiltonian of the system contains kinetic energy, and that Hamiltonian will commute with momentum, so energy will be discrete. And since we are dealing with symmetric potential well, so for symmetric, V minus x is Vx, and wave function we can calculate as same, and we will get under root 2 by a sine n pi by a. There was x, so here will be translated by a by 2, so x a plus by 2. One more thing, that this value under root 2 by a cos n pi by x upon a for n is equal to 1, 3, 5 for odd quantum numbers, and this will be in sine for even quantum number. So wave functions corresponding to this odd quantum numbers, so these are what? Even. Let it follow symmetric. These wave functions are symmetric, where these are for antisymmetric. Symmetric, that is psi minus x is equal to psi x, and for antisymmetric this is psi minus x is equal to minus of psi x. So this is what we have discussed. Square potential, that is infinite square potential, and for that is for asymmetric and symmetric potential. Now in next video we will deal with finite square potential. Thank you.